My clock shows 10:29, not yet 10:30. But anyway, good morning to everybody. I'm Jean Goubeau-Larec, the chairman for this session. And our first speaker for that session is Jonni Virtema. And we're going to wait a few seconds perhaps. Now my wall clock time is 10:30. So Jonni, if you want to share your slides. Thanks.
Good. So should I start, or are we still waiting for a bit?
No. I think it's now time.
Okay, thanks. So this is a joint work with these people, Miika and Juha from Helsinki and Martin from Hanover, and we are now talking a bit about complexity of different fragments of second order Boolean logic, and I'll keep it quite simple and will not go to much technical detail. So if you're interested in technical details, then you can check those from the paper. So I'll start from what's essentially, I believe, everybody here knows. So from these canonical complete problems for NP and P space. So we have Boolean formulae, so Boolean variables and connectives, and then we know that Boolean satisfiability is an NP complete problem. So whether a Boolean formula is satisfiable, and then that can be extended with quantifiers. So there exists some value for the variables for all values of variables, and then we get to quantified Boolean formulae and then to check whether this kind of formula is true is a canonical P-space complete problem. And then what can be done is that this first order part or this quantified free matrix here and here can be changed to conjunctive normal form or conjunction of three disjuncts, so 3 CNF, and it's still NP complete and P space. So this is a well-known complete problems for these classes. And what might be a bit less known is the so-called dependency quantified Boolean formula. And the idea there is that we still have this kind of quantification of variables, but instead of this kind of linear sequence of quantifiers like for all x, there exists y for all y, and so on. We have this kind of non-linear dependencies. So for each existence of quantifier, we can write down explicitly those variables where it depends on. So for example, we can say that Q1 depends on P1 and P2, and Q2 depends only on P1, for example. And this QBF, there we can also have it in that kind of setting, but there the constraints are linear. So that's that the dependencies of Qi plus 1 have to include all those that are for Q1. And so if we allow this kind of non-linear dependencies, then we get a complete problem for non-deterministic exponential time. And what we can do here is still again assume that this matrix here is in 3 CNF. Okay, so what can we do to make this a bit more simple? Well, if we assume that the matrix theta here or here or here is a Horn formula, so this kind of in conjunction of implications where the antecedent here is the conjunction of proposition, and the consequent is a single proposition. Then we get that both Horn satisfiability and quantified Horn satisfiability are in polynomial time. And maybe what's more surprising is that also this nonlinear dependency quantified Horn formula drops from next time to p time when we have Horn formula here. Okay, so you can also think it differently a bit, such that essentially in this kind of Horn formula we have some kind of existential first order quantification. So we quantify Boolean variables in a first order way. But in this kind of DQB, in this DQBF and DQ Horn, what we essentially are quantifying are Boolean functions. And essentially we shift to some kind of existential second order formulae in this kind of Boolean setting. And what can we then ask is that what happens if we make this this quantification more complex? So what did we see here now was that we had these two kinds of things we could do for this CNF formula to increase or reduce its complexity. So we could restrict the matrix from CNF to Horn, and then we got a drop on complexity. And then we can also make the quantification a bit more complex. So here we shifted from existential first order to existential second order, and there was an increase in complexity in the CNF case, but not in the Horn case. So now what we can do is to think a bit more, what can we replace this CNF, or what can we change this quantification to, and can we then see what happens to the complexity of this kind of a variance of SAT then. Yeah. So the idea in this talk is to have a complex second order quantification, but still have a simple quantifier-free structure, and then see what happens. Okay, so let's define a logic. So this is just essentially second order logic on Boolean domain. So what do we have is that we have functions, and if the arity of functions are 0, we call them propositional. Otherwise, we call them proper function variables. And then the second order logic is just the syntax of second order logic. So we have quantification of these Boolean functions here, and then we have Boolean connectives, and then we have this kind of atomic statements, which are now this kind of term constructions. And this is now what we call SO2, or second order logic on Boolean domain. And the semantics of the logic is what you would expect this to be. So essentially, ExistF says that, okay, we have an interpretation for F such that phi holds. So there's nothing odd here, just a definition of second order logic. Good. So what do we know about this logic is that the truth problem is complete for this complexity class. So alternating exponential time with polynomially many alternations. And now we can think this DQ horn as an instance of certain formulae in this logic. So we have this quantification of Boolean functions, and then we have the quantification of propositions, and then we have some matrix. And what kind of fragment this DQ horn is? Well, so these functions come from essentially scalarization of the existential variables. So what we have is that we have no quantified alternation in secondary logic, so we are in sigma 1 fragment, and then the clause here are horn, and then what we also restrict how these functions can be used. And what we say is that there is no nesting of function terms, and each functions must have unique sequence of arguments. And an SO2 format that has this kind of properties now correspond to this DQ horn. Okay, and then we can also consider other prefix classes of this SO2. So sigma k just means that we have k second order quantifier blocks that start with an existential, and then we have one extra propositional block that differs from the last second order block. And pi k is, of course, we swap existentials to universals. And again, what is known here is that that sigma k formulae are complete for the kth level of the exponential hierarchy. Good. Okay, so what we knew now from this horn set and DQ horn is here, but another restriction would be to assume that the matrix is in 2CNF or Krom form. And then what we get in 2-set and quantified Krom is that we get complete problems for NL. And then the question is, what do we get for this quantified Krom formulae? And this is one question we answer in this paper. Okay, so this is just to remind you what is horn, Krom, core. So horn was this kind of implications, and we have only one positive literal here, and Krom was just 2CNF, and core is then this kind of implications that both sides have at most one. So it's both horn and Krom. And now we have these two restrictions for this SO2 formulae, which is uniqueness, which means that each functions must have unique set of parameters, and simpleness, which means that each parameter has to be propositional. So no nested functions. So here is an example of these, but those should be essentially clear. And now this DQ horn is now this sigma 1 fragment, this horn unique and simple. Okay, so then we get this kind of table. We can consider this kind of horn, Krom, and core clauses. We can consider the second order quantifier prefixes sigma k and pi k for any k. And then we can consider whether there's uniqueness or simpleness. And now what I will just quickly show is how we show that this unique and simple Krom sigma 1 is in NL. And idea is that it is essentially a derivative of the classical method of showing that these other Krom logics are in NL. So we start with this kind of implication graphs. So for each literal, we have a point in the implication graph, and then we put an arrow in the graph if a clause here creates this kind of implication. For example, here this says if P is true, then Q must be true. So there is an implication from P to Q. And if negation Q is true, then negation P has to be true. So we have an implication of here. And then what is known that a two-set, it's enough to check that there is no vertices such that we have both a variable and its negation in the same strongly connected component. And when we go to quantified Krom, then we also have to deal with dependencies that arise from variables, and it makes things a bit more complicated, but this is also the classical approach. And then when we go to this DQBF or dependency of this graph, the sigma 1 Krom, so when we quantify functions, then there will be a bit more complicated dependencies. So in principle, in the SAT, in the QBF, we only have to think about how can variables depend on other variables. And there it comes from essentially from a variable quantification order. But when we quantify with Boolean functions, we want to know when the function is dependent from another function, then it's a bit more complicated. So if we have something is a parameter of something, then it depends on something, or if something is quantified before something and all the parameters that is there is also there, you get this kind of dependencies. But it's a bit technical, but it's in the paper. But in principle, what we get is a procedure how to construct satisfying assignment for the functions and variables. And then we get that the truth of unique simple Krom one is NL complete. So then what we get is some things here. And then in most cases, what we get is that the sigma k is complete for the kth level of the exponential hierarchy, and the pi k is complete for the kth level of the hierarchy. But the other interesting cases are here. So the truth of simple Krom or core sigma 1 is p-space complete, and the simple Horn sigma 1 is x-prime complete. But again, the proofs can be found in the paper. And then we get this kind of table of results where most are as you would expect, but we have these kind of interesting cases here and here, and also some open cases here, which is now the dual Horn case here. Okay, so what we did here now is that we saw that the SAT QBF and DQBF are increasingly intractable, and while when we restrict those to Horn clauses, then all of them drop to polynomial time. And then we need the same kind of analyzation for different fragments of this SO2. And this is now one open problem that we are left with. Okay, thanks a lot for attention.
Thanks, Jonni. Are there any questions? We have 5 minutes for them. Let me remind you. Okay, Arno. Oh, no, Arno is clapping, sorry. So let me remind you before we start questions that you still have the possibility of asking the authors any questions you may have in the speaker's corner after the session. In the meantime, I don't see anybody raise their hand. So let me ask a very silly question, Jonni first. I'm wondering, there are plenty of applications of SAT solving nowadays, and even of QSAT or QBF solving. Are there any real-life applications of any of the classes you're presenting us? Or is that just an intellectual research, which is perfectly fine to me, by the way?
So what I've noted in the literature that nowadays they are starting to do this kind of DQBF solvers.
Mm-hmm.
So in this kind of DQBF setting, things are starting to be usable.
Mm-hmm. So those are interesting spatial cases that occur in practice, you mean?
I don't know what you mean by they exist in practice. What do you mean by?
Yeah. Okay. Don't worry. Don't worry. Yeah. I was a bit curious. I mean, the idea of constructing those graphs is a well-known one, but yes. I was actually left wondering what you would have to do next to handle the more complicated quantified cases. You said it was in the paper, but I would still like to have a bit of an idea of that, right? So here on this slide, I understand that you have a few more conditions to check, including the fact that you have no dependency cycle, I guess.
Yeah, so the point is that then you have this kind of, so once you do this kind of graph, then you have connected components. And some of the components have universal function quantifiers and some of them don't have. Now, and another question is, how does this kind of how do those interact with each other? So you cannot really have like a path from a universal one to a universal one, for example, because that will break things.
Okay.
So
my question was more about slide 22, where you said the details would be in the paper. And so in particular, you can't use that kind of algorithmic technique that remains in polynomial time or, to solve these. So what's new there?
I have to say that I don't remember currently how did we prove these. So this
is that really technical, or is there any simple idea we could get from?
Well, many technical things was done by Martin, who now left the academia, but it's been a while since I've checked the details. I simply don't remember how these work. Actually,
okay.
Check.
No worry. So I seem I have failed to stimulate any question from the audience. But if that's so, well, we'll just have to wait for 2 more minutes. And let me thank you, Jonni, and the authors.
Good morning. My name is Nicolas Peltier. I would like to present our paper, Decidable Entailments in Separation Logic with Inductive Definitions Beyond Establishment. This is joint work with Mnacho, Echenim, and Radu, Iosif. We are interested in a logic called separation logic, which is useful in program verification in order to reason on mutable data structures. So the logic allows for the specification of recursive data structures by means of inductive construction rules, which can be provided by a user. More precisely, the syntax is defined as follows. We have a set of variables, constants. We consider atoms that can be emph, standing for empty, equations between variables or constant, or this equation, and points to atom, which states that a variable or constant x refers to a record of variables or constant y1, yk. We have predicate atoms, which are used to denote recursive data structures of arbitrary size. We use the usual disjunction and existential quantification, and we also use a special connective denoted by a star and called separating conjunction. Such formulas are interpreted in structures defined by a given infinite set of locations or memory addresses. A function S called store, which is a function mapping every variable or constant to a location, and a function H called heap, which is a partial finite function mapping some locations to a record of locations. And a location is allocated if it occurs in the domain of the heap. Formulas are evaluated as follows. The evaluation of equations or this equation is as usual. For points to atom, we say that such a formula here is true if the location that corresponds to x is the only allocated location and refers to the record of locations that corresponds to y1, yk. Emp simply states that the heap is empty, namely that there are no allocated locations. Disjunction and existential quantification are evaluated as usual. And for separating conjunction, this formula here is true if we can split the heap into two parts that are disjoint and that are such that the first part satisfies phi 1 and the second part satisfies phi 2. For predicate atom, we assume that every predicate symbol is associated with a set of rules of this form here. These rules may be provided by a user. And given this set of rules, we define an infolding operation on formulas by stating that the formula psi may be infolded into a formula psi prime by replacing an occurrence of such an atom here by a corresponding formula phi, in which we have replaced the formal parameter xi by the corresponding actual parameter yi. And then we say that an atom is true if this atom can be infolded into a formula psi containing no predicate symbol, which is true in the considered interpretation. Then we can show that all the formulas are actually equivalent to disjunction of formulas of the following forms. We have an existential quantification of a separated conjunction of atoms. Such formulas are what we call symbolic heaps, and we are interested in solving entailments problem for such symbolic heaps. That is to say, given a formula phi, psi 1, psi n that are symbolic heaps, and given a set of inductive rules, we want to check whether all models of phi are models of one of the psi I. As an example, we can define the list segment from x to y here using these rules that are here, and we can also, by adding appropriate disequalities in the definition, define list segments that are non-cyclic. And we can ask whether a non-cyclic list is also a list. And of course, we can define many other examples, such as trees, doubly linked list, and so on. We know that such entailment problems are undecidable in general, but they are decidable for a specific class of inductive definitions, which is actually quite large. The proof is based on a reduction to monadic second-order logic on graphs with bounded tree width. But the proof gave no effective algorithm and no precise complexity bound for this problem. So the considered class of inductive definitions is defined by the following conditions. we have the first condition, which is the progress condition, which states that every rule must allocate exactly one memory location, which means that it must be of this form here, where only one points to atom in the right-hand side. And the variable x1, which is allocated by the rule, is called the root of the atom, and it must be the same in all rules associated with predicate P. Then we have the connectivity condition, which states that the set of allocated locations has tree-shaped structures, meaning that if phi contains an atom here, of this form, then necessarily the root of this atom must be connected with the variable x1. And finally, we have this last condition, the establishment condition, which states that every existential variable occurring in the rule must be allocated eventually in the formula phi. Then we consider what we call PCE problems, so entailment problems satisfying progress, connectivity, and establishment. More recently, a 2x time algorithm was defined for such entailments. Actually, there are two versions of the algorithm. The second one has a larger scope, and we were also able to prove that this bound is actually tight. The problem is 2x time hard. However, the establishment condition is actually rather restrictive because it forbids what we call bundling edges, in the sense that if a location occurs somewhere in the heap, then necessarily it must be either allocated or associated with a variable. This forbids, for instance, rules such as this one here, in which we have this variable x prime, which is not allocated in the right-hand side, and which may, for instance, refer to some structure outside of this list. So it is natural to ask whether this establishment condition can be removed. And in this paper, we show that it can be replaced by a new condition which is less restrictive. So this condition is called E-restrictiveness, and basically the idea is to simply forbid equations and disequations between variables. So we assume that if you have an equation x equals y, or this equation x not equal to y, then either x or y or both must be a constant. This forbids, for instance, a rule of this form here, because here we compare two variables, x prime and z. But this rule here is allowed because we compare x prime with c, which is a constant. So we have what we call PCR problems, entailment problems satisfying the progress, connectivity, and restrictedness conditions. We can prove the following theorem, stating that the problem of checking the validity of PCR entailment is decidable and is in 2x time. And more precisely, we can show that the complexity is doubly exponential with respect to the size of the rules and symbolic heaps, but only simply exponential with respect to the number of rules and symbolic heaps. Now I will briefly go through the proof of this result without entering too deeply into the technical details. The first step is to apply a kind of normalization of the entailments and the considered systems. First, we get rid of free variables by replacing them by constants. Then we also remove all equalities. For instance, if this equality involves an existential variable, then we can simply delete this variable and replace it by its value. More importantly, we also ensure that all the parameters of a given predicate occur in the heap of the model of this predicate. So this forbids, for instance, definitions such as this one here, because here we see that y does not always occur in the model of p of x and y. If we apply this rule here, for instance, y does not occur in the right-hand side. we also ensure that the set of allocated parameters is the same in all unfoldings. For instance, this forbids rules of this form here, because we see that depending on the rules that we apply here, y may be allocated or may be non-allocated. The general idea to enforce these conditions is simply to replace a given predicate by a disjunction of a predicate. For instance, in the previous example, we can replace predicate B by a disjunction of two predicates defined by appropriate rules. So the second step is to focus on a particular class of models that we call normal, and a structure is said to be normal if all the variables are interpreted as pairwise distinct locations, except those that are equal to a constant. So if we have two variables with two distinct variables with the same value, then they must be equal to a constant. And we can show that PCR entailment is valid if every normal model of the left-hand side is a model of the right-hand side. So the very basic intuition of the proof is that every model that is not normal can be obtained from a normal model by applying some morphism on separation logic structures, and this morphism preserves the truth value of all E-restricted formulas. So it is sufficient to focus on such class of models. So the final step is to construct abstract representations of normal models, and the idea is simply to represent a given structure by the set of formulas that it satisfies. But of course, this set is infinite in general, so we have to restrict ourselves to a finite class of formula. So this is done first by giving an upper bound on the number of roots occurring in the formula. We assume that the formula contains at most n plus m roots, where n is the maximum number of variables that occur in a rule, and m is the maximum number of existential variables occurring in a symbolic heap. And also, we assume that all the variables are interpreted as distinct locations, so we consider only structures with injective heaps, and with this condition, all equation or this equation can be removed because they are either trivially true or trivially false. So these two conditions ensure termination in the sense that we can show that the number of formula with a bounded number of roots and no equality is finite. And also they are sufficient to test entailments, because to test that such an entailment is valid, we only have to check that the representation of every normal model of phi contains one of the psi I. And the only remaining problem is how to construct such representations. And to do that, we use a bottom-up approach with a least fixed point computation algorithm. And to do that, the only difficult point is that we have to compute the disjoint union of structures. And to do this aim, we need to add new predicate symbols in the signature. So these predicate symbols are used to denote the form of heap difference. For instance, if we have this entailment here, then we have to check that this entailment is valid. We have to remark that every model of this atom here actually also satisfies R of X if we add a disjoint structure that satisfies Q here. So this is written as follows, using this special operator here, which is similar to the separating implication for those of you that are familiar with separation logic, but it is not exactly equivalent because here the definition is not purely semantic. It depends actually on the unfolding tree of this predicate symbol. We can show that for any atoms here, this formula can be actually defined inductively using a set of inductive rules. So there is no need, to extend the logic, but we need to extend the set of rules and predicates. And afterwards, separating conjunction can be undone by using a form of modus ponens. We can just chain this implication here. So, for instance, if we consider this separating conjunction here, we can deduce this conjunction satisfy a formula R of X. Thanks to these predicates, the abstract representation of the models of a formula can be constructed inductively, starting from the best case, which is the points to atoms, and using inductive cases that corresponds to existential quantifications, predicate symbols, and separating conjunctions. And of course, the harder case is the case of separating conjunctions. We can also prove this result that state that PCR systems are strictly more expressive than PCE systems. And more precisely, any PCE entailment can be reduced into a conjunction of PCR entailment problems. And the reduction is actually exponential, but the size of the rule increases only polynomially, which means that the 2x time upper bound is preserved by the reduction. So the intuition of the proof is that after normalization, the only atoms that are problematic are these equations between existential variables. So they are of this form here, x not equal to y, where x and y are existential variables. But precisely due to the establishment condition, we know that x and y must be both allocated. And we can also show that they must be allocated in disjoint part of the heap, which means that they are necessarily distinct in all unfoldings. So to sum up, we started from a result that states that entailment is decidable and in 2x time for separation logic formula that satisfy the progress, connectivity, and establishment conditions. And we show that we can replace the establishment condition by a new condition called E-restrictedness, which is strictly less restrictive. And we provided a new 2x time algorithm for this entailment. As far as future work is concerned, so it is natural to ask whether we can go further and get rid of the E-restrictedness condition. And actually, this is not the case. In a paper which is currently under review, we showed that this is not feasible in the sense that the entailment problem became undecidable if we simply get rid of this condition. But we can show that we can relax some of the conditions, in particular those concerning the left-hand side of the entailment. And finally, we also would like to handle theory reasoning in this context, which is, of course, essential for application. So either by using a theory for locations, or by using additional sort for data with their associated theories. So this concludes my presentation. Thank you for watching this video.
Thank you, Nicolas. Are there any questions? So let me ask one first. You said your algorithm was 2x time. Is the problem 2x time complete?
Yes, it's also 2x time hard. We showed this in a recent paper.
So oh yes, you had
time complete. Yes,
you had mentioned it near the beginning, if I remember well. Yeah. Okay, thanks. Yeah, another thing was that strange, almost magical wand. Okay, so the thing that looked like the magic wand. I would like to understand it a bit better. For example, would it be correct to say that the implication, P1 star P2, etc., then implies Q? It must have some connection with the clarification. So P1 funny arrow P1, P2, funny arrow, and so on, funny arrow Q, right?
Yes, there is some connection. Basically, the idea is that we consider the unfolding tree that corresponds to the right-hand side, and we remove some part of this tree. So we remove the part of the tree that corresponds to the left-hand side. So it differs, for instance, from the usual magic wand, the separating implication, because if we replace an atom by some atom that is equivalent, but not exactly the same as equivalent, defined by the similar set of rules, then we do not preserve the truth value because the unfolding tree will differ. So this is the basic difference between the standard magic wand and this special implication. But otherwise, it behaves rather similarly. So the idea is the same. It's to have to show that some formula hold in an extension of the heap by some disjoint structure.
Mm. Any question? I still have one, but don't count on me for all questions. So let me ask my third question. It's still on the kind of magic wand you have. There was an old technique that had been developed, if I remember well, by Kim Larsen initially, then by other people such as François Laroussini, called compositional model checking. And compositional model checking meant essentially, if you wanted to verify that a formula phi holds of say a parallel composition of processes, then instead of building the parallel composition of processes, so instead of verifying that P1 parallel P2 satisfies phi, you'd try to verify that P1 satisfies a formula that you build from M2 and phi, and that is meant to be what you expect, okay? So it looks like it has a lot of similarities with your ideas of having this operator.
Yes, I'm not familiar with the techniques that you mentioned, but I think that might be some relation, at least in the IDB, because here the problem is to okay to reduce this say to compute from a global formula to decompose the global formula into the different subparts in order to allow for testing the property by referring only to the specific to each specific subpart.
Thank you. We'll have a final question by Radu Iosif.
Hello. Yeah, actually, it's a remark to your or maybe additional answer to your question relative to composition of processes. The thing is that separation logic and the semantics of the separation conjunction is defined in what is called an abstract separation algebra. So this is an algebra that has several properties such as cancellativity or more generally aggregativity that makes the composition to behave like disjoint union. Okay, and my point is that composition of processes is in general not a good separation algebra. So it does not have these properties to make it behave properly as what you would expect from the separating conjunction to behave like. And for this reason, there is an extension of separation logic called concurrent separation logic, which has this composition of processes defined in a way that there are no data races. So they just abandon any computation when the data races occurs. And with this restriction, they guarantee that composition of processes becomes a separation algebra, but in general, it's not. Maybe that kind of clarifies a bit the.
Okay, thank you, Radu. I'm sorry, I have to act as a host, and we're starting to be late. So it's time for our next speaker. Let me thank again Nicolas and Radu for his clarifications. And now the next speaker is Benedikt Pago.
Yes. So this is today's second talk on the topic of choiceless polynomial time. So early in the morning, we saw a positive result concerning its expressive power. And now I'll say something about its limitations. But first of all, what do we mean by choiceless computation in general? So in the classical setting, computation is described by Turing machines that manipulate bits on a tape. But in the finite model theory world, we view computation as choiceless computation, which means we perform the computations directly on the finite structures by means of logic. So in particular, we don't translate the structures to binary strings like in the Turing machine setting, but we work on them directly. And this computation by logic has the key property that it has to respect all symmetries of the input structure at any computation stage. So that means choices among indistinguishable objects are always forbidden, hence the name choiceless. And this is also different from the classical Turing machine setting, because on a Turing machine, you always have this string of bits. And of course, you can distinguish, let's say, bit number 1 from bit number 2. So the symmetry invariance does not play a role in classical computation. And of course, the question that arises is, in how far does this symmetry invariance of the computations limit the power? And the question that is connected with this, that we also saw earlier in the morning already, is this. So does there exist a logic that captures p time? And so this means we're searching for a logic that can express exactly those properties of finite structures, which can be recognized in polynomial time by a Turing machine on a suitable encoding of the structure. And it's maybe important to say that in the setting of linearly ordered structures, this question has already been solved. So all the logics you see here in this yellow box do actually capture p time if you only look at finite structures with a linearly ordered universe. So the question is only really interesting in the case where the structures are unordered, because that's when the symmetry invariance of these logics has an impact. And so I would say this problem, does there exist a logic for p time, is far from being solved. But here's an overview of the current state of research. So this is a complexity landscape of logics which are contained in p time. So that means the evaluation problem for each of these logics is in p. So for each fixed sentence in such a logic, evaluating its truth value in a given finite structure can be done in polynomial time in the size of the structure. But the difficulty is, of course, the converse. So how to express every p-time decision problem in a logic. So as an example, consider, for example, the problem, is a given graph connected or disconnected? So this is clearly in p-time, but for example, in first order logic, you cannot express it by a single sentence for locality reasons. And therefore, stronger extensions of FO were developed. So these fixed point logics that you see in the middle in this picture, but even those logics have been separated from P. So the main candidate logics that still remain for capturing P time are rank logic and choiceless polynomial time. So for these logics, it's not yet clear if they're equal to P or not. And I'm only concerned with the logic CPT here. So a bit more about CPT and its history. So it was introduced in 1999. And since then, various things have been found out about its expressive power. So on the positive side, what we know is it is strictly more powerful than fixed point logic with counting, which is quite a strong and well understood logic in P. And also, as we heard earlier today, there are some classes of structures where we know that CPT does capture P time. So for example, if you look at structures with some padding or structures with abelian or dihedral color classes, as we now know. And also what's interesting for certain versions of the so-called CFI problem, those can also be solved in CPT. Yeah, so the CFI problem, I'll get back to that later. But for now, let's say it's just a very hard problem for logics and often used as a benchmark. So yeah, for this problem, we do have some partial positive results. And on the negative side, we don't know that much. But maybe most interestingly, Rossmann showed that CPT cannot define the dual of a given finite vector space. But this is a functional problem. So this is not a decision problem. And yeah, it's not clear how this negative result tells us anything about the limitations of the power of CPT for decision problems. But that's actually what we are after. So again, the main open problem here is, does CPT capture polynomial time on all finite structures? And capturing p-time means solving all decision problems. So my contribution is also a negative result for a functional problem, similar to the one by Rossmann. But I will tell you in the end that this is a problem which has a strong connection to a decision problem as well. Yeah, so my result is this. So no choiceless polynomial time program can define a pre-order with color classes of at most logarithmic size in arbitrary hypercubes. And the questions I will answer in this talk are, yeah, I'll say a bit more about CPT. What is this? Then I'll give you a general argument why CPT cannot define certain objects. And that's also the reason why this theorem holds. And then I'll say a bit more, yeah, what are these preorders with logarithmic color classes? And in the end, I'll give you the motivation for this. So why is this interesting, and in how far is this connected to a certain decision problem? Okay, so first of all, about CPT. Yeah, it's actually quite complicated to give a full and precise definition of it, but that's also not necessary for the purposes of this lower bound result. So I'll just give an overview. So actually there are various ways how you can formalize CPT. So there are different logics which are equivalent to it. So originally it was defined as an abstract state machine model, but there's also something called polynomial interpretation logic, which is completely different, but yet has exactly the same expressive power. And finally, there's also what's called BGS logic. And this is maybe closest to a programming language. So this is a language where you can you have terms that allow you to manipulate hereditarily finite sets. Yeah, so these are finitely nested sets whose atoms are always elements from the input structure. And these are also the general data structures of choiceless computation here. And to give you some example syntax, you see below some primitives of this BGS language. So basically you can perform all the set theoretic operations. You can form pairs of sets and construct new sets in that way. You can take the union over a given set or do these comprehension things. So for those of you who know Haskell, it's a bit like Haskell, but instead of lists, you're always manipulating these nested sets. Yeah, and I think this should suffice for now. So now we take a more abstract view on this logic CPT and disregard all the, let's say, implementation details and focus only on the properties of CPT which are relevant for this non-definability result that I presented. So we just say CPT is formalism for symmetry invariant computations on polynomially sized hereditarily finite sets as data structures. And these are very basic conditions because the symmetry invariance simply follows from the fact that CPT is a logic, and every logic has to be symmetry invariant. And of course, this polynomial size bound on these sets is also unavoidable because the evaluation of CPT programs should be possible in p-time. So of course, there must be a polynomial size bound on the sets that a CPT program may construct. And to give you an example for this computational framework, so let's say we would like to compute a linear order on some given input structure. And in this case, it's a very simple graph with 3 vertices. And now the stages of our computation will always be these nested sets. So we might start at vertex A on the left and construct this easy set, and then traverse the graph from left to right, for example. And in doing so, we would produce such a sequence of nested sets. And this final set on the right is indeed a suitable representation of a linear order on this graph, because every vertex occurs at a unique nesting depth in the object. So this also shows that these nested sets as data structures are quite powerful, because they can actually represent any kind of combinatorial object that you would like over the input structure. But so far, this computation is not symmetry invariant. So in the input structure, there is an automorphism that swaps the vertices A and C. So if you now disregard the colors, so you can basically mirror this graph in the middle. So a choiceless computation, so the output of a choiceless computation would not be a single linear order in this case, but it's actually this set that you see there, and that contains two linear orders, which are automorphic images of one another with respect to this swapping of A and C. So this is what CPT always does. So it constructs such nested sets, but they're always closed under all automorphisms of the input structure. And from this, it's not so hard to derive a general argument why certain objects are not definable. So one can observe that from the symmetry invariance, it follows that any nested set X that you would like to compute must necessarily be computed together with all its automorphic images, as you see in the example. And so this is called the orbit of X, the set of all automorphic images. So this follows from the symmetry invariance. And if you now also take into account this polynomial size bound, then you can see that any object whose orbit size is super polynomial with respect to the input structure size, such objects can never be computed by any CPT program. And actually this line of argument is quite strong, because it doesn't depend on any details of the logic CPT. And actually, even if you, let's say, you extended CPT with some non-deterministic guessing mechanisms, then this would still be true. Okay, and so with this in mind, let's get back to this theorem that I showed you earlier. Now, I still haven't told you what these pre-orders are. So basically, a pre-order on a set is just a binary relation that partitions the set into color classes. So these are the classes of indistinguishability, basically. And on these color classes, the pre-order is a linear order. So in some sense, a linear order, a pre-order is an approximation to a linear order up to these color classes. And now here's again the main theorem. So if you look at pre-orders with small enough color classes, so of at most logarithmic size, then these are not definable in hypercubes in CPT. And now the proof is you simply have to compute a super polynomial lower bound on the orbit size of such pre-orders. Because from what I said on the last slide, it then follows that no CPT program can define such an object. And here, for example, you see in this picture the three-dimensional hypercube. And now, let's say we fix an arbitrary pre-order on its vertex set. In this example, with these two color classes, red and blue. And now, one can see if you now apply some automorphism of the hypercube, then that might destroy the pre-order and change it. So let's say we mirror now the hypercube in the middle and swap the vertices according to these red arrows in the picture. Then this will also change the pre-order and swap the color classes. So in general, in order to prove this result, one has to fix an arbitrary pre-order and then count the number of distinct pre-orders that you can generate from it by applying any automorphism of the hypercube. And from this, it follows, the result follows. So in short, these pre-orders are undefinable simply because the number of automorphisms of the hypercube is quite high. And now finally, I still would like to tell you what this has to do with non-definability for decision problems. So let's come to this so-called CFI problem. So this is often used as a benchmark for logics in finite model theory. And for example, it also separates fixed point logic with counting from P. So this problem is in P time, but provably not in FPC. And therefore, it's also reasonable to believe that it might be a problem which is not in CPT, but we don't know that yet. And yeah, so what does this problem look like, roughly speaking? So instances of the CFI problem are always obtained by applying a certain construction to a fixed family of underlying graphs, as they are called. And so in our example, let's say the underlying graphs are hypercubes, and then the CFI graphs on them are obtained by replacing the vertex gadgets with certain, the vertices with certain vertex gadgets, which we treat as black boxes now, and the edges are replaced with these edge gadgets here. And up to isomorphism, there are only two different CFI structures that you can construct, and they're called even and odd. And so this is the even CFI graph, and the odd CFI graph is the same, but now one edge gadget has been twisted. And the CFI problem asks you, given a CFI graph, is it the odd or the even one? So you have to recognize which edge gadgets have been twisted. And the main point I want to make here is that structurally, the CFI graph and the underlying graph are very similar. So they also have the same symmetries. So that means the undefinability of these pre-orders on hypercubes is also true for the CFI structures on them. Yeah, and now this is interesting for the following reason. So the strongest result we have currently for solving CFI in choiceless polynomial time is this. So if you assume that the CFI structure comes with a built-in pre-order with logarithmic color classes, then the CFI problem can be solved in CPT, because there is a CPT algorithm that essentially exploits these color classes and their small size. And yeah, this was the motivation for me to show that in general, you cannot use this algorithm. So if you look at the CFI problem on unordered hypercubes, for example, then it is impossible to, out of nowhere, construct such a fine pre-order that would allow you to apply this theorem. Yeah, so as a consequence, for solving CFI in general, we need new techniques which require less, let's say, symmetry breaking objects. Yeah, so that's basically it. So what we saw is choiceless polynomial time is a potential candidate logic for capturing p-time. But we have now also some evidence that we can say a potential problem that might separate CPT from P is the CFI problem, in particular on unordered hypercubes. Because the amount of symmetry in these hypercubes makes it impossible to define a fine pre-order on them. But this seems to be necessary, at least for now, to solve the CFI problem. And I would like to quickly add something about work in progress, which is now new and not in the paper. So I have now found out that actually it is not necessary to have such logarithmic pre-orders in order to solve the CFI problem. But I have found new algorithms which can do without them. So for example, instead of such a pre-order, it is also sufficient if someone gave you, let's say, a tree decomposition of the graph without any order and small bags, then you could also solve the CFI problem in choiceless polynomial time. So let's say this pre-order based approach to the CFI problem seems to be a dead end, but there are other ways which might lead somewhere.
Thank you. You've even managed to keep to catch up on the delay we had. So are there any questions in the audience? Yes, Arno. Let me. Yes.
So if it's the should be the case that CPT works fine for decision problems, but not for functions. Is it then really a completely satisfying answer, or would then the next step be to ask, okay, what kind of logical framework would we need such that definability in the framework matches computation for functions?
I haven't really thought about that, but I mean, I guess from these functional problems, you could turn them into decision problems, right? So if you have understood the case for decision problems, then I think that's already quite good.
Yes, Arno? Ah, yes.
Sorry, I muted myself and then I lost the opportunity to ask a follow-up directly. I think the problem here would be that that turning a function problem to a decision problem, for example, by saying say yes if the case bit of the answer is 1 and say no else. That's sort of talking in a very central way about the encoding of the answer as a binary sequence somehow. But if you have a functional thing from some structure to some other structure, it is much less obvious whether sort of a symmetric function can be broken down into decision problems which are symmetric too. So
yeah, okay, I see what you mean.
Hence, functions may be really a real thing on their own, which isn't just composed of decision problems here. But,
I don't know if this question is really being studied that much in finite model theory, so maybe, yeah, that might be something to think about.
Okay, any other question? Well, the next talk is going to, oh yes, Adam.
Hey, hi Benedikt.
Hi.
Good to see you again, and thanks for the talk. I just had a question about this follow-up work you talked about at the end. So when you talk about auxiliary structures of these graphs, are you talking about, firstly, are you talking about the auxiliary structures on the underlying graph on which
yes.
Okay, and then my question is, like, my understanding was that in the original family of CFI graphs, the family has like unbounded tree width, right? So there aren't like small tree decompositions in general. So
yeah,
is there? So is this work on using small tree decomposition sort of like orthogonal to that, or yeah?
Well, it's just something that of course wouldn't work in the most general case,
right?
But there are still, I mean, the CFI problem is still not solvable in FPC as long as the tree width is greater than constant. So this would be interesting, for example, for structures where the tree width is, I don't know, logarithmic or doubly logarithmic or something small but not constant. Then it's still an interesting problem because it's not solvable in FPC, and we don't know yet about CPT.
Okay. Yeah. Okay. I get that now. Thanks.
Yeah.
Thanks. So thanks to the speaker again, and we'll move on to the next talk by Arno Pauly.
all right, thanks. Shall I start directly? Or?
You can.
Okay, so I'll be talking about joint work with Christina Gaßner from the University of Greifswald and with Florian Steinberg. And we have been looking into what happens if you sort of add the ability to compute the Lebesgue measure of certain sets of real numbers as a primitive operation to a certain model of real number computation, and to see how much power that gives. I would view that in a bit as a kind of real number version of sharp P, because well, in sharp P, if you can decide membership in a suitably bounded set in polynomial time, ∠P lets you count how many things are in that set. And here we'll be dealing with the case where our set isn't a set of finite strings, but it's a set of real numbers. So rather than counting, we're looking at limit measure. And it turns out here that we do not just get an advantage in being able to do computations faster, but we actually increase what we can compute in the first place. So we sort of only need to do computability theory, not complexity theory. So there are sort of two notions of real number computations that you can come across if you just look at the literature. There is the notion of real number computation coming from computable analysis, and the one-sentence explanation of what a computable function is in that context is that the computable functions are the natural continuous functions. With that, I mean that, first of all, every computable function is a continuous function. Once you figured out what the right topology is that you should be using. And if you come across a continuous function, because you're genuinely interested in understanding this particular continuous function, it's going to be a computable function. The sort of non-computable continuous functions are those that you build on purpose because you want a non-computable continuous function. Say you just build in the halting problem into the coefficient of a polynomial, something like that. The other model is following work by Bloom, Shoup, and Smale. There, the idea is to sort of, well, pretend that the floating point data type we get in the interpreted programming language is actually modeling the reals and just running with that. So, for example, that would be ignoring the fact that we have only bounded precision, ignoring the fact that floating point addition is not commutative, not associative, and has sort of not really any algebraic properties in common with real number addition, but just looking at an idealized picture where we can add real numbers, multiply them, test them for being equal, find out which one is smaller, and so on. What we get then is that the BSS computable functions are piecewise polynomials where the pieces themselves are definable by polynomial inequalities. I could talk a great deal about which of these models is better and more natural and so on. I won't. I will just say that sort of, as you can see from my terminology, I think that if we're actually asking what should computability of functions on the reals mean, we really should go with the formula to get the right answer. But the second one is still a natural model of something, and understanding better what's happening in that model is still a quite good idea. And there are fields like computational geometry where people really like to use these BSS models, so knowing what is and what is not computable there is a very interesting goal. And the sort of model we are starting with here is actually the BSS computations too. but we will see that once we do with them what we're planning to do, which is let them compute the Lebesgue measure of certain sets, we are actually kind of merging both streams, and it suddenly makes a lot of sense to bring in the formalism of computable analysis to better understand what is going on. So a BSS machine is essentially a kind of register machine with two types of registers. We have the index registers, where we have natural numbers in them. We can do the usual things you would expect a register machine to do with natural numbers, and the fact that we are using them as index registers means that we can do things like write a natural number in one of those registers and then and then do some swapping around of the other registers. Those other registers are carrying real numbers in them. And what we can do with those is we can add them, we can multiply them, and we can test which one is bigger. And then we have our usual register machine programs with one more final twist, which is that we can have commands inside our programs that let us write a real number into a particular register. That's something that you wouldn't need in a classical discrete register machine program, because there you can construct all potential contents just with a suitable program. We can't do that here, so we need to sort of have some building blocks. To make the comparisons we're going to do later nicer, it does make sense to restrict us to the case where we are only placing computable real numbers into registers in one step. But if you want to do away with that constraint, you can essentially relativize all the results that we have with respect to some arbitrary oracle. And then what you get is just with that constraint gone away. One important thing that we can do is there are we can build universal BSS machines that take essentially a program apart for the constants that program is using as one natural number plus a tuple of reals containing the constants the program want to be using, plus another tuple of reals containing the input we want to be running that program on. And then a BSS machine can decode the program from the natural number, access the constants as it needs those constants, run what the coded program would do, and get the output that we should get there. So that's all working sort of nicely as a model of computation should. And what we're adding them is we now give them the option of having a new command inside our register machine programs, which in one step computes the Lebesgue measure of a BSS decidable set coded via the program that actually does that job. To be a bit more formal, sorry for the huge chunk of text on these slides. So we are adding this new lambda command. When the program reaches the lambda command, we look into the first index register. There we find the Gödel number of a BSS machine. That number may be referring to some constants, which will be the first however many constants we need real number registers. We then also look at the second index register where we see what is the dimension of the input we want to be running that program on. Now the semantic constraint is that the coded BSS machine must hold for every input from the unit hypercube of the corresponding dimension and say either yes, that point belongs to that set, or no, it doesn't. In that case, we get the Lebesgue measure of the subset of the unit hypercube accepted by this BSS computation. And if that's not true, for example, if the BSS program diverges on an input where it answers 1/2 or something like that, then if essentially the entire computation fails, it doesn't go anywhere. We don't have a valid input. And then our question was, okay, how can we describe what kind of functions these BSS plus lambda machines can actually compute? And well, we found out that we could describe this class of functions computable in this framework in various different ways using various different languages. And I'll show you the theorem first and then go a little bit more into what the parts mean. So one thing we observed was that there is another command we could have instead added to our BSS computations, and that is of being able to compute the limit of a BSS computable sequence, where we know that this BSS computable sequence converges fast. So that and getting the measure of a decidable set is the very same. But then we also saw that we could actually describe this class of functions very conveniently by using the language from computable analysis, where we have a notion called reducibility, which is essentially just the kind of many-one reduction for computable functions on these types like real numbers and so on. And the sort of, despite the fact that we haven't built that in any obvious way, the functions computable by these BSS plus lambda machines are closed under composition with computable functions in the computable analysis sense, and we could identify a sort of complete problem in the variety degrees for this class, which is essentially about sorting infinite binary sequences multiple times. There also is a way how we can enhance the model of computation we would be using in computable analysis to get that very same class. And the last description of this class of functions is more in a descriptor set theory kind of style, because we can see that if we can, that the functions in this class are exactly those where we can partition the space of finite tuples of reals into pi02 parts, and then on each part that function is computable in a uniform way. So if you have the input and you know what part of the partition you're in, then you can compute the answer. So to say a little bit more about what these individual things mean, this controlled limit now sort of is set up in a similar way as a lambda command, but now we are interpreting the Gödel number of the BSS machine that we get there as a machine computing a function from n to some vector for reals, and the constraint is that these reals converge quickly. For example, the n's and the m's have to be at most 2 to the minus n minus m apart, And then what we get from that is whatever the limit is. And doing that is kind of gives us the very same thing as being able to compute the Libet measure of something. Sorting binary sequences, infinite binary sequences sounds a bit odd, but the idea just is if there are finitely many zeros in your infinite binary sequence, you move those finitely many zeros all to the front, followed by the all those infinitely many ones which are left. Whereas if there are infinitely many zeros, then you have, well, then you never reach the part where you start writing one, so you just output constant zeros. And this problem sort diamond, that's again the kind of the idea there is we have again a register machine containing, say, infinite binary sequence and reals all as basic types. But now we can do all computable operations, tests, and so on. And we can sort these pointer space elements. So that is a sort of rather nebulous concept, but it sort of can all be made very precise. And what we get there is that it can compute exactly the same functions on those real number types as we had with all these S plus lambda machines. The final model is one where we have a machine which can make one guess. It's for our case, it will be a natural number which we guess, and then it can either keep running forever, write something infinitely often, which jointly constitutes an infinite output. Or it can only write finitely many times on the output tape, in which case we completely that just doesn't count. If it does write infinitely often, that needs to be a correct answer, and it always has to be something we could have guessed that makes us do a correct answer. And then that's item 4 here, just to show the theory once more. If we can guess a natural number and then use this weak non-determinism, we again can do the very same functions. Now, something which sort of I found a bit surprising here is that we are actually considering the particular algebraic structure we're getting on the reals by the fact that we've used multiplication and addition as basic operations. And for the very last one, I will show you what happens if we start with something else.
Arno, you've got 1 minute left.
Yep.
Okay, fine.
Which is if we would, for example, start with saying, let's put in all computable operations at the start and then add our lambda command, we get something which is just as strong as iterating this lambda command and taking the functions we had on the previous step. And now let us compute the measure of a set decided by those previous ones. And that thing is also just as powerful as if we would take this ability to compute the limit of a VSS computable sequence, but we drop the constraint that the limit needs to be converging fast. And for all details, I'm afraid I'll have to point you to the paper because I need to stop now.
Thank you, Arno. Questions? Did that click? I don't know. So there's a question apparently. Oh no, sorry. Oh, sorry. I was, okay. So I had no really precise question, but I was wondering whether there was any connection between the BSS plus lambda model and whatever Martin Escardo, Alex Simpson, and others had done to integrate to include integration into real PCF, and whether these computational models had anything to do with each other.
I sort of, if you're sort of only integrating computable functions, that's still a computable operation, provided that they're sort of suitably bounded. Once you are integrating functions where the integral essentially isn't forced to exist, but it just does, you can get non-computable reals as outputs. So you could, for example, approximate a semi-computable real from maybe below by just putting a spike here that does the first step, then you put the next spike and so on, and sort of just keep adding smaller and smaller spikes as you need to sort of grow up there. That gives you a computable function from the reals to the reals with a well-defined integral, which is that non-computable real.
So that's a way more expressive model, yes. So the BSS plus lambda machine model is a way more expressive model then, yes.
And well, no, that can't get you any pointwise non-computability. Because if sort of all your inputs are computable, you always get a computable output. Sorry, since sort of the only non-computability you get is in a sorry, I wanted to go in the other direction here. The only non-computability you get here is if you look at item 5, is in being able to do a partition into Pi02 pieces. But then on each piece you're still producing some computable output. So that's, I would say it's still a natural class of functions, as witnessed by us being able to get various different characterizations, but it's also a bit of an odd one, because usually if you want to increase beyond computable, you'd move to something else.
I see. Thanks. Looking whether there would be any other questions in the audience. I don't think so. Well, don't forget that you can still ask the authors anything you want, well, about their talks mainly, in the speaker's corner, starting from now, okay? And have a nice lunch, and we reconvene at 1:50.